you can see the split screen. So this modelling comes up a lot. I think any topic we do throughout Pure where it finishes with a modelling subsection, we mustn't just sort of let it just sort of not happen, because I'd say they come up a lot in the actual exam. So we must try and work through as many of these as we can. So I'm going to give 2 lessons to this. That will then be the end of the chapter, apart from the mixed exercise. So what I propose to do is I won't give lesson time to the mixed exercise, but I will give you a bit of a break from differentiation, just so you can have a bit of a catch up if you want. And so what I'll do, I'll set the unit test, but I'll give you a long time to get it done. So like a fortnight or something, so you can choose to work your way around the mixed exercise beforehand. Don't try and do all the mixed exercise, but just do a sort of selection, because we've been doing this a while. Do you remember? It goes right back to that delta stuff where we were doing first principles. So I want to give you a bit of time just to dot around and do a few of the questions from the mixed exercise. But those of you who feel confident, I want you to have a chance to crack on with the unit test. So anyway, let's have a look at this bit, please. So we're modelling with differentiation. So up to now, we've been doing dy dx. Okay, so we've been differentiating y with respect to x. Okay, so it's the rate of change of y with respect to x. Now that's a very pure thing. I now want to put that more into a practical terms. Now we've seen this before when we would have done IGCSE in practical terms, when we were doing the kinematics, when we were doing so just to remind you, when we were doing GCSE, we would say that the rate of change of displacement of distance with respect to time was velocity. So you have already seen it in a practical terms. We did that at IGCSE. Harry, I appreciate you won't have done that. Okay, so the rate of change you're covering ground, the rate of change of covering distance with respect to time is velocity. And again, you would have seen that the rate of change of velocity, how quickly velocity is changing. Well, that's what acceleration is. Okay, so we will cover all of this again when we do mechanics. So Harry, you haven't seen this, don't worry, we will go over this and build on it. But for those of you who did the IGCSE, you know, this is your one exposure so far to differentiation in a real life context. Okay, now just look at the one at the bottom. We're saying the volume of water in this water butt is constantly changing over time. If V represents the volume of water in the water butt in litres, and T represents the time in seconds, you could model V as a function of time. Okay, so we can work out the rate of change of velocity over time. So if we had a velocity equation, we could differentiate it to work out the rate of change of the velocity. So let's just have a look at this example. That's really following on from that water bottle type of thing. Given that the volume V of an expanding sphere is related to its radius by the formula V equals 4/3 pi r cubed, find the rate of change of volume with respect to radius at the instant when the radius is 5 centimeters. So velocity equals 4/3 pi r cubed, as we know, that's the velocity of the sphere is. We go and differentiate that with respect to time. So multiplied by the current power, 3 4s are 12, 12 divided by 3 is 4. Pi is just a constant, so that stays where it is, and reduce the power by 1, we get 4 pi r squared. Sorry, I said with respect to time. That was obviously a mistake. We're differentiating velocity with respect to the radius. Excuse me. Okay, the radius was our variable. So we've got 4 pi r squared. So that is the rate of change of the volume. Okay, so at the precise time when the radius was 5 centimeters, for a split second, so just picture there's your sphere filling up. When you're at that split second when the radius was 5, how quickly is it filling up? And that split second, it's filling up at 314 centimeter cubed per centimeter of radius. Right, now, example 22, okay? Now, this is a classic question, and this is where we're going to be moving on to, okay? You will classically get quite a complicated first principles part A that you will give it your best shot at, okay? And we will look at that in a moment. You will give that your best shot, but it will always be a show. It will always be show that volume or whatever equals something. So even if you make a right pig's ear of part A, you can go on and do B and C, which are always easy. So you mustn't get to one of these questions and think, oh my God, I can't do these. Give A your best shot. If it works, that's great. If it doesn't, don't worry. But you must make sure you go on and do B and C, because B and C start off with what you've been given as a fact in part A. All right. So anyway, let's just have a look at this one out of interest. So we're told this tank has got no top. So it's obviously got one, and it is, what is it? It is a cuboid. So it's basically got three rectangles. It's got the, obviously the side, left-hand side, the back of it, and it's got the basement, the base of it, okay? And it's got the two ends, okay? So the two ends, because it's square-based, you can see from the diagram, the two ends are obviously the area of the two ends, which are x by x. We've got two of those ends, so that's 2x squared. And we've got the three rectangles. So looking at the rectangle that I've shaded, obviously the area of that rectangle is base times height is x times y, and we've got three of those. The two sides and the bottom of it, it doesn't have a top. So that is our total area. We're then told in the question that the total area is 54. Rearrange that to make y the subject. So we've now got our first formula in terms of y and x, and we've done that from the area. Now we happen to know that the volume, obviously the volume of any prism, is you take the area of the cross section, so the area of the end bit, which is the square, which is x times x, and you multiply that by the depth of the prism. So the volume is x squared y. We've then gone and substituted in what y is from above to give us an equation for v purely in terms of x, and then we've simplified it. So that part A, you might crack it or you might not, but it doesn't matter if you don't, because when you move on to B and C, these are very straightforward, all right? So on this slide now, when we move, this slide, yeah, that you can see already, this is easy. You know what the volume is. You've just been given it. Whether you proved it or not, you were given that in part A. So just differentiate that. So that's easy, all right? That's easy to differentiate. To add a maximum or a minimum value, you just set the differential to 0 and you solve. Now, that's just very easy maths, all right? An easy differentiation, easy to set it equal to 0, easy to solve. Now, x is a length, so clearly it can't be negative. So the length is 3, and then you substitute that into the volume to work out what the volume is, okay? So we've worked out that the volume is 36. Now, we know that is either a maximum or a minimum volume. And then, do you remember what we were doing before? To work out whether it's a maximum or minimum, you take the second derivative, you work out d2y dx squared, all right, in this case d2v dx squared. So you go back to your your dv dx. Remember that was, I'm just circling it in red. Has it come through yet at your end? Yeah. So we've got our dv dx. Differentiate that again, and we get minus 4x. We've worked out that x was 3, so substituting 3 into that, we get a negative second derivative, okay? And because the second derivative is negative, okay, that's when it is a maximum. Remember, we're saying when the second derivative is negative, that is a maximum point. So because d squared v dx squared is less than 0, it is a maximum. And that's it, folks. So I would like us to spend the next two lessons, today and the next lesson, working our way through exercise 12K, please. So I'm just going to freeze this, stop recording rather, and then obviously feel free after that to unmute if you've got any queries.